Welcome to the Going Native on Android talk. Let me just tell you a little bit about myself. And also, before I do that, I just want to give you a slight disclaimer. I just recently finished the slides. I yet have to optimize them for this sort of screen, and the fonts may not be as good or as big as they need to be. There are plenty of seats up here if you guys want to take advantage of that, if it's going to make it easier for you to see. So, with that said, my name is Aleksander Gargenta. I also go by the nickname of Sasha. I am now part of Twitter University, where I help transform Twitter into a learning organization. I've been using Android since 2008, ever since the old G1. I've been developing since 2009. I've been teaching it since 2010, and actually for the last couple of years, I've been focusing mostly on the internals of Android, so low level, not even application space. That said, I also happen to run the San Francisco Android user group. I'm the founder and actually I'm one of the co-organizers, and I'm also involved, I'm also founder and co-organizer of the San Francisco Java user group. And we have regular events, very much like this one, and where you guys are welcome to attend for free and learn about what's going on in Android world. Prior to Twitter, I was with Maracana, where I was the CTO and instructor for quite some time. Anyway, this screencast will be published to our YouTube channel when it's done, just so you know. So, I guess why are you here? Presumably to learn how to go native on Android, but what does that really mean? So one of the big reasons why people say they want to use native code in Android applications is to take advantage of existing code they've already either written or comes from someone else that they wrote that code. So code reuse. Performance optimizations also are often cited, although that you should really think hard whether you use that as your sole claim to reasons for going native. And even worse is the language preference. Some people just like say, hey, I'm a C++ developer and I want to do just that. I want to learn how to use Java. We'll come to address some of these concerns as we go deeper into the slide deck, just so you know. So the other reason why I think it's interesting to learn about going native on Android is to better understand how Android itself works, because as you will see, Android essentially is composed of many layers, and the bottom layers are very important to the essential functionality of the platform, and they're all pretty much written in C or C++. And the top layer written in Java needs a way of talking to them. So once you understand this, you also understand how Android works. And then, because it's cool, that's kind of just goes without saying, I hope. So why not go native, right? I actually wanted to, before I tell you how, I want to tell you why you shouldn't do this. Even though it seems kind of crazy, why am I saying about this? Well, first of all, complexity. Let me actually make this font slightly bigger. Complexity and brittleness. In particular, when you are essentially implementing the Java to native bridge, as you will see, you're often dealing with things like reflection-based APIs. You're dealing with memory management, which leads to memory leaks, memory corruption, which lead to crashes, security vulnerabilities like buffer overruns. The performance issues, which is kind of weird. I said earlier that going native is something that people do in name of performance. Well, it turns out that just the bridging of going from Java world into the native world, so some code written in C or C++, is actually a very rather expensive proposition. Just that method call is actually really expensive. So for simple code, it's actually much better to write it in Java, in pure Java, and most likely with the just-in-time compilation that's been part of Android since Froyo, it'll actually run faster. So be very careful when you go native, just for the performance reasons. Limits portability. So as you guys know, Java is inherently portable. That was one of its essentially founding features. And whereas native code can be written so that it can be ported to different platforms, but that adds additional complexity. It's not free out of the box. For Android, it's not as big of a deal because kind of the APIs are rather limited or set. So since those APIs tend to be already portable, you tend to not do crazy things. But you still may occasionally run into memory alignment issues between, say, ARM and x86, which is an important platform to target. MIPS being another one. And then most Java APIs most Android APIs are Java only. So if you wanted to, for example, create a system service or a broad PCC or a content provider, or interact with a bunch of system services that Android ships with, you pretty much are limited to doing it in Java. Not even just in the Dalvik VM, but really in Java. So it's not about C versus Java, the virtual machine. It's really Java versus any other language, including, for example, say Scala or something else that you may want to run instead of Java. So Java is the main mechanism how you consume APIs in Android. And then finally, security restrictions are pretty much the same. So you don't really get any benefit of being quote-unquote native in terms of what you can do on the platform, because the security in Android is enforced at a process level, not at the virtual machine level. So circumventing the virtual machine doesn't buy you anything. So then the answer is, or I guess the final question is, well, when should you then go native? So the biggest reason, the biggest win, if you will, to justify the increased complexity and the brittleness and everything else that comes as a result of it is the code reuse. So if you have some piece of code that either someone else wrote and it's been proven to work well and you've used it successfully elsewhere, you shouldn't just go and rewrite it in Java just because it's a fun exercise. You should try to reuse it if you can, especially if that code is self-contained and you can basically create a nice thin wrapper around it. Sometimes though, it's not only for legacy code. For example, if you want to reuse code across different platforms, like say iOS and Android, actually going native is, believe it or not, a portability solution. It kind of seems weird, but that is a way to actually have portable code across different platforms. And then if you do know that some code is extremely self-contained, very low memory footprint, and you can basically isolate it well, so you can build an API that's rather coarse-grained, so it doesn't require too many interactions, or I should say transitions, context switches from the Java world into the native world, then such as, for example, signal processing, physics simulation, data transcoding, those things lend themselves well to essentially implementing it natively. Although Android also ships with something called RenderScript, which is another interesting API to explore for this sort of use case. So then, what does it really mean going native? This is really the diagram that has all these boxes and arrows and whatnot that hopefully I'll explain over the next little slides. But basically, you'll see that we have an app that, oops, sorry, wrong key. That's not what I wanted to click on. We have some Java code that may sit over here that basically wants to, sorry, I guess my thing doesn't work for drawing on screen, that wants to use some code that basically sits over here, and we write some JNI bridge that essentially enables that code to be wrapped, and I'll explain in a bit how. And then we have this thing called Ndk, which enables this JNI bridge to be compiled and packaged together so that we can reuse the code. And then we have these libraries that sit down here that basically give us or implement the features that basically make everything glued together. So I'll go through this step by step. So this is kind of what we want, right? We have some sort of an app that wants to talk to some sort of a library that already presumably exists. So we would like to call it, but because these are two different worlds, Java world and native world, that doesn't happen. So if we try to do this, there's no real mechanism to make it possible. We know that on the development side, we have Java C or something like JDT that compiles our code to basically something that will eventually be packaged and run on Android. But what happens on this side? That's not clear. So what is the first step? The first step is generally we create some sort of a Java quote-unquote native API. What that really means is we expose methods in Java world that are simply denoted, or I should say qualified as being native. You literally use the keyword native, and then you don't provide the body. It's kind of like creating an abstract method or an interface that basically the implementation is going to come from elsewhere. And your Java app now calls this quote-unquote native app, native API that's still written in Java. This API can't call or somehow magically bind to the library that we want to use. We still need another piece. So what we typically do is we then use a tool that is part of the JDK called Java Age, which then can be run against this Java native API to essentially, and this Java native API is just a class, to produce a C header file that essentially defines the prototypes of the functions we're supposed to implement, which will then somehow magically map onto these native methods that we previously exposed. That's at least one way of doing it, although I'll show you another. And then what we do is we write that JNI bridge. So JNI, for those of you that don't know, stands for Java Native Interface. It's been part of Java since I believe 1.1, if not earlier. And it's basically a set of, think of semantics, or pretty much actually, there are two things that are part of JNI that are important. One is the JNI.h, which is a header file describing common functions and data types, as well as a few utilities, like for example, JavaH. Well, what we are doing here is we're creating a library, and I'll show you this in an example in a bit, that basically implements these native methods by utilizing the JNI.h functionality, and then internally calls the library that we actually want to use. So basically, JNI, for the purposes of this discussion, is an API that enables us to write C code, native code, that acts as a bridge between the Java world and the C world. The native code written using JNI is not supposed to implement any sort of business logic. It's not supposed to basically be the code that you write. It's supposed to just be the bridge between one world, Java, and the other world which you want to use, which is native. Just so you know, JNI in normal Java land is also used in the reverse way. You can actually use JNI to embed virtual machines inside of native code, rather than within Java code call upon the native code. So it can be used in a reverse direction, although that doesn't really apply to us here. So the question though is, how does this actually work or bind to or glue together at runtime? So what happens is, when we start our application inside of Adobe PM, and our application basically calls this native API, this native API will generally be responsible for issuing a call that will logically load this library, which is essentially a shared library, which will contain both the JNI glue, the code that we write, plus the code that we want to use. That's the code that presumably was given to us by someone else. These two things are generally combined, fused together into a single shared library. The virtual machine internally will do something like DL open, and it will essentially load it into the virtual machine space, and then allow us to bind to it. I'll explain the binding process in a little bit later, but essentially, after this step is done, these native APIs, these native methods, are somehow magically mapped to the functions that we've implemented inside of this JNI library. So, who provides this JNI.h? So JNI.h, just to kind of remind you, is this header file that describes the functions that we can use to basically bridge from Java world to the native world. And I'll explain what sort of problems we have and why we need this bridge. But at runtime, these functions are implemented with something called libdvm, which is not even important for you to remember, but there's something in Android that basically provides the functionality. It's part of the Dolby virtual machine. So, however, JNI.h is, just one thing. That's basically, just gives us basically the simple set of functionality to bridge the gaps between two language environments. But what about everything else? What about, for example, opening files, creating sockets, doing string manipulation, that sort of stuff? Standard C stuff. Where does that come from? Well, Ndk, which I keep on kind of referring to, but hopefully by the end of this you'll understand what it is. I'll tell you right now that it stands for Native Development Kit. Ndk, one of the things that it includes is basically a set of stable APIs. These are header files that are guaranteed to be there in the future versions of Android. So what that means is that if you, for example, want to do I/O, you can do and include standard I/O. Or if you want to do, for example, string manipulation, you can include string.h, which are standard libc, basically, or standard C library functionality. But in addition to the standard C library, Ndk also provides these additional basically header files, like for example, a way to log to the Android logcat, or the way to manipulate Java bitmaps in C, or a way to create a native activity, or a way to, for example, plug into the looper, or a way to do OpenGL calls, or a way to do math or compression, or loading other libraries, or sound manipulation, and so on and so on. Of course, this may seem like an exhaustive list, but it's actually rather limited. For example, SQLite, even though we know it's there on Android, it's not on this list, and we can't legally assume that it will be there in the future, right? Or libSSL or things of that nature. they're there, but they're not really exposed by Ndk, so therefore we may try to use them, but at runtime they may not physically be there for us to use, right? Or they may change. So who implements all this stuff? Well, in the side of the Dalvik VM, or I should say a part of the Android stack, includes a whole range of native libraries that specifically implement these header files. Like, so for example, JNI Graphics implements this thing called bitmap, and this libandroid implements basically this native activity storage manager and a bunch of things of that nature. Like libc implements all this other stuff at the bottom. libm is the math stuff, and so on and so on. So these are the shared libraries that will be automatically bound to our process as necessary, or linked to our process as necessary, and made available for us to basically do what we want to do. That's standard C stuff. But the point is, these libraries are guaranteed to be available. That's part of the Ndk promise. Now, this is not a full story. There are additional libraries, like for example, the libssl, libsqlite, libbinder, libui, and so on and so on. There's a range of additional libraries that exist in the system, which maybe we may be tempted to use, but really shouldn't, because again, they're not guaranteed by Ndk to be available in their current form in the future. So they're there to support Android, and if you were building, for example, a native Android app that's burnt into the ROM, and you could make assumptions about what's going on to the ROM, then you can do whatever you want to. But if you're building something that's supposed to port across the billion Android devices that are out there, then you may want to think about how you actually, what sort of assumptions you make of the platform. So finally, we want to compile this, right? So of course, having these libraries and everything is nice and dandy, but how do we actually get our code to be available and inside of this APK that will eventually ship? So that's where the Mdk Build tool comes into play. That is basically a little simple script, literally a shell script, that utilizes one of the tool chains that's part of the Ndk. So for example, a tool chain in Ndk may include GCC compiler, G++, make, LD, AR, strip, and a whole range of things that you may be used to from doing native development in, say, Linux. So this basically means that Ndk is self-contained with respect to the tool chains that it needs. And they're essentially cross-compilers. So for example, my Mac, I have cross-compilers for x86, for ARMv5, ARMv7, and MIPS, all packaged together into Ndk. So to kind of summarize the Ndk part, Ndk is basically a tools chain, or I should say is a set of tools and APIs that are made available to you as a developer. And of course, that includes things like the documentation, sample code, and whatnot, which we're not going to go into. But this is basically the general approach to going native on Android. Now, I actually wanted to just talk about this in abstract. I wanted to show you some code, and hopefully in doing so, you'll get a better appreciation for what's involved and what are the real challenges of doing this. Because so far it might be easy because it's just a bunch of hopefully pretty pictures. So what I did is I actually created this application called Exify, which is essentially wraps this native library called JHead, which has been around the block since 2001. It was written by Matthias Mandel, my bad. He's actually a fellow Canadian. And this library is used to extract and even manipulate EXIF information in JPEG files. And this information includes things like ISO and aperture setting, shutter speed, flash information, that sort of stuff. This code, this application, is obviously an Android application, wraps this shared library, or I should say existing library, which is again the use case that you think is lends itself best to Ndk, or I should say native. And this application is available on our GitHub page, or I should say GitHub repo, and you can just grab it, run it, compile it, and test it out. This is generally what it will look like when it's up and running. So basically, you'll select some sort of an image. It will, once you select it, it will actually extract the thumbnail that's embedded inside of the image. So it will not take the entire image and resize it and somehow fit it into the bitmap. It will actually extract it. That's part of the JNI code that I'm going to show you. And then it will go and literally dump, or I should say extract the contents of this EXIF information and give it to the Java world, which will then display it on this page. This is not even the whole thing. This is actually a scrollable list, but of course this is just a screenshot from my computer crash. So I'm going to have to restart the emulator to show you this later on as to how it actually works. But you can try it out. Anyway, that's the app that I'm going to basically go through. Just to kind of tie back to the quote-unquote big picture. So before, I was saying we had the, these Java code we want to write and C code that we want to use. Well, let's make it real. So here we're going to have a library called libjhead. That's the code that we want to use. And then what I'm going to do is I'm going to write a single C file, it's going to be rather long, called jhead.c. It's actually going to have this long prefix that will act as the bridge from the Java world to the C world. This library, I will not change anything inside of it except for the makefile. That's the only thing that I'll basically adapt to the Android needs. And one thing I'll do is I'll actually compile this library statically so that when this code gets compiled, it will essentially compile against the static library, so at the end of the day it will be just one happy little shared library that will basically contain both the JNI code as well as the jhead code. And then on this side, I'll have an activity, just a single activity called main activity, that will basically utilize this thing called Java class called jhead, which will eventually go and use this. Now, just to give you a little bit of a disclaimer, I did not go through the trouble of doing this in proper threading manner. So, for example, all of this is being done on the main thread, and there are all sorts of issues with that because it involves I/O. But thankfully, it's only reading, so it's not as bad, and this is only for demonstration purposes. The rest of the stuff is pretty much the same. So I'm not going to go into the details of how again the rest of the stuff applies. I just wanted to make it real as to kind of what we're going to go through. So how would you get started? So basically, the first thing you would do is normally download or use an IDE. And before I would say use any IDE, I don't really care, but actually in the version R22 and above of the Eclipse ADT toolchain, they added support for Ndk right into the Eclipse plugin. In fact, part of the ADT bundle includes not only the Java support and the Android support, also includes the C++ support. So you have nice, easy, editors, and you can do essentially jump to declarations of things. And it has built-in not compiler, but built-in checker, and so on and so on. It's actually a really nice development environment for the whole thing. Now, I understand the world is moving towards Android Studio, but unfortunately, Gradle doesn't support Ndk well, at least not right now. I do know that they're working on it, and as a result, Android Studio doesn't have a good story for Ndk as well. So going native inside of Android Studio is possible, and I've done it, but it's ugly, hackish, and just not as pleasant as it is doing it in Eclipse. So that's step number one. Step number two is you download Ndk. You can literally drag it, just unzip it, untar it somewhere, depending on the platform. And one thing I'd like to do is add it to my path. Then inside of ADT, or Eclipse, you configure the Ndk location. That's actually, by doing so, Eclipse is able to do builds right within the Eclipse environment. And then we create an application project. In this case, I call mine Exify. And I set a minimum API level to what I think, the platform I want to target. The one thing about the API level is that, remember that Ndk set of APIs, the scatter files that I said Ndk supports, basically these things? Well, these things have grown over the past, years or releases. So in the beginning, there weren't as many of these. So for example, it was Gingerbread that added support for native activity storage manager, looper, sensor. It is the Jelly Bean or 4.3 that added support for OpenGL 3.0, like ES 3.0. So for example, if you were targeting anything prior to API level 18, you wouldn't have access to GL3, as an example. So you got to be careful about the assumptions you make when you actually, or I should say, the relationship between the library availability and the minimum level that you choose here. So one other thing that you do, and this is again unique to Eclipse or IADT, is that you can actually add native support to your project. When you do that, you'll automatically be prompted to specify the name of your library, which you haven't even had yet. But when you enter the name, Eclipse will generate some pseudo C++ file and create a makefile for you. And it'll create it in a directory called JNI, which is basically what we want. That's part of the kind of the unwritten, well actually it is written somewhere, but it's part of the documentation or semantics that it will expect all your native code to be under this directory called JNI by default as part of your project directory. Of course, I don't care about that auto-generated C++ file, so I would delete it, and then I would add support, or I would keep this Android.mk file, although I don't care about the contents, I just care about the file because this will be our make file. So that's the basic stuff. So what about JHead? Well, JHead, literally I would just go to the source, to the website of JHead and download the tarball. I would uncompress it somewhere, and then I would copy only the C and header files to the JNI directory. I don't care about the make file, I don't care about any other documentation files, I don't care about any sort of autoconf stuff. I would just copy the raw source. Then I would basically have to go and create my own make file because the one that comes with JHead is just not good enough for us. Now, if you have a complicated library or project, there is in fact a tool, I think it's one called Androgenizer, if I can remember it correctly, that basically will take a make file that was written to, with autoconf in mind and convert it to something that Android expects or Ndk expects. But thankfully, JHead is not as complicated, so we don't really have to deal with that. So once we have JHead, we want to now really convert its make file. So this is where we're really exposed to the Ndk for the first time. So this is the make file. Whoops, this is the make file that we'll be using. And inside of this make file, what we would enter is this. Now, what does this all mean? Well, we can kind of start from the bottom. Well, this basically means we're going to be building some sort of a static library. Okay, so that's where it said. We're going to package JHead as a static library because it'll be packaged in yet another shared library. This thing called local module specifies the name of the library. If this was AOSP, Android Open Source Project, it would have other meanings, but we're not going to worry about that. And you don't specify the .so, and you don't have to specify lib in front of it. When this gets built, this will automatically become, if it was a static library, it would have been libjhead.so, or in this case, because it's static, if it was a shared library, because it's a static library, it will be, libjhead.a as an archive that will then be embedded elsewhere. This specifies the set of files that will basically make up our, source. You don't have to specify any of the header files. The compiler is smart enough to follow the includes and include them as necessary. So we just specify the C files. One thing that I did in particular, though, is I omitted specifying this file called mydewalt.c, which was in the original make file that JHead came with. And the reason for that is, well, the main reason is because it doesn't compile for Android, but really it's because it's Windows specific, and I really don't care about it. So I just literally omitted it. And that was it. Now, I'll come back to this in a moment. Let me just mention this, local path. So local path is basically a setting that specifies that all of these files are relative to basically whatever this evaluates to, and this evaluates to the current directory where basically the make file itself is located. Right? So this is just a macro that's part of the GNU make that will just give you back the current working directory, or I should say the current directory of the make file, and so these files are just relative to that. Of course, you can have subdirectories if you want to organize things differently, but I just wanted to point out that this is how I chose to keep it simple. Now, one more thing I didn't mention is this, clear vars. So clear vars is basically just means clear any variables that start with local underscore, except for the local path. And in this case, it's not even necessary that we use it, but generally clear vars is used when you have multiple build targets, one following another. And because these things are essentially global variables, you don't want global variable from one target to affect something happening in the next target. And we will have actually other targets in a moment, so you'll see how they fit together. So clear vars basically just flushes out the registers, if you will, or zeroes out the global variables. So hopefully that will make sense. If you wanted to learn more about what sort of things go into the make file, you can click on this link later when you actually access when I post these slides, or you can just look in the Ndk directory and you'll actually see there's actually a document that says, oh, this is what the Android Ndk file is supposed to have. So now we want to compile it. Okay? So far we really just created one file, but now we actually use Ndk. So there's two ways to do this. One way is to go into Eclipse and simply say build all. This, because you've previously configured Eclipse to use Ndk or to know about Ndk, will automatically run Ndk Build, which will then look by default. It will know to look for a file called android.mk in a directory called JNI. And once it finds it, it will execute all the targets that exist in that file. And because it will find this one target that says build this static library, it will just go and run it. And it'll actually spit out some results in the console. The other way to do this is to actually do it from the command line. This is assuming that you have Ndk in your path. Then all you need to do is cd or change to the directory where your project is and run Ndk Build -all. What that will do is we'll basically do the same thing and you can see the results. Now it does give us this stupid little warning that says, hey, this platform version, blah, blah, blah. Actually, this I think is a bug. And so a way to fix that bug is to create another file in the JNI directory called application.mk. In this application.mk, we'll specify other things, but for the time being, I just want to get rid of this warning. And so what I'll specify is app_platform equals to the platform that we specified as our minimum SDK version. Okay? This we would have specified when we created our project for the first time. So whatever your manifest file says about your minimum platform version should be here. This is totally redundant, unnecessary in my mind. Why do they give us a warning? I don't know. I think it's a bug, but this is a way to get rid of the warning. So if you wanted to clean everything, you can just go and say project clean, and you can do another project build all, or you can just do ndk-build space clean, and it will just do a clean for you. Now, one of the other problems, actually one of the things that may not have been obvious from this, because I don't know how many of you are familiar with this term called thumb, but basically thumb means this shortened 16-bit instruction set for ARM. This was something that ARM did way back when to basically make their instructions be even more compact. So, but that's beside the point. What this really means is that this application or this code will only be right now compiled for ARM. And what if we wanted to target, the Chinese market where MIPS is more popular, or, soon the North American market where, Intel is expected to explode. So the x86 instruction set. We don't want our code to be discriminated against different platforms. So we want to be inclusive. How do we do that? Well, basically, one way to do this, coming back down here, is to, inside of this application.mk, this was the file that I just showed you, we create our simply another flag called app ABI. ABI stands for Application Binary Interface, and we say all. If we wanted to, we could have said app ABI equals x86, or x86 and MIPS, and it would just target those two platforms, or x86 MIPS and ARM v5, and so on and so on. Or all just says everything that's supported. And as of the most recent version of the Android Ndk, it supports 4 different APIs: ARM v5, ARM v7, x86, and MIPS. If we now then go and rebuild everything, what we will see is that it will basically, for example, if you look for A files inside of our generated object local directory, you'll see that this libhead will now have been compiled 4 different times. And if you, for example, look inside of, say ARM v5, you'll see that individual files have been compiled into their own object files. And if you do a file on one of these, you'll see, for example, that the one from the ARM directory is in fact a 32-bit ARM, essentially shared library. Okay? Of course, this is not the final thing that we'll actually end up using, but I just wanted to kind of give you an idea of how this works. All right, so this was compiling JHead. Now, the fun starts. This is now we get to the JNI part, the real deal. The first step is, and this looks a little weird, and this, I guess my formatting is all screwed up in this resolution. Should have tested better. But anyway, the first thing that I did is I created a class called JHead. I generally recommend separating the code that will have the native methods from your application code. Like in Android, they violate this rule all the time. They basically take some, say, Java service, and they slap a bunch of native methods inside of that service. And it then becomes a little kind of hard to understand where the interface is between the Java world and the native world. I actually like to separate it out, as opposed to putting the native methods that will eventually be my API inside of the activity. I set them up inside of a separate class. So this class is just called JHead, for obvious reasons. And then I create, and let me make this slightly smaller just so you can kind of see it. so it doesn't quite wrap around. We created two methods, one called getImageInfo. So given some sort of an image by file name, and this is an absolute file name, this is going to give me a map of strings. So basically I'll have a bunch of tuples. One's going to be a key, let's say aperture, and the value will be whatever, f3.5, that sort of stuff, or f/3.5, that sort of thing. I could have used something else. In fact, it would have been nicer if I created an actual real class called camera or image info and then specify a bunch of things, but that would have just been more work, especially when it comes to Ndk, and I'll explain why. And then I have another method called getThumbnail, and this method basically gives me a byte array. And the reason why I did these two is just because these two methods lend themselves to a lot of different things we're going to have to deal with in J9. Now, two things you'll notice here, or actually three things. In fact, four things. Let's start with the first one. First, these methods are native. And because they're native, they have no body. That's the API that I was referring to. Second thing you'll notice is that these methods return, or I should say, throw exceptions. C code doesn't throw exceptions. C code goes and returns -1, and then you have to figure out what the heck that means. Java developers don't expect -1, so you don't directly map C API to Java API, you basically map the expectations of the different developers. Then you'll also notice that these methods are synchronized. That seems a little odd. The reason why they're synchronized is because in this particular library, this particular library uses a lot of global variables that are mutable. And because they're mutable, you cannot have two concurrent instances or two concurrent threads basically using the library at the same time. The library shouldn't have been written that way. They never thought of this use case. So whatever, we have to deal with that. I actually haven't tested whether synchronize of native methods works. So there's a possibility that these two things cannot actually, I mean, the compiler doesn't complain, but it's possible that synchronize somehow gets abandoned when there's a native method, so I should have tested it. If that is the case, then you would just have to create another method that basically acts just as a wrapper for the native method. So this is something that is just, a little bit of a warning. And then the last thing is this thing called load library. This is basically part of that diagram where the Java code was responsible for loading the native code. So notice that we specify the name of the library by some logical name. In this case, I call it jhead_j9, which is a common naming convention. Now, I don't specify where this library is, and it's not even important that you know where this library is. But just to know, if you care, if you look on a modern Android device, you'll see it under /data/app-lib/ and then the package name of your app, and then you'll see the library. The library will usually have lib in front of it, then whatever name you see here, plus.so. Now, this is the name by which we're reading it, but we haven't even specified where this library is going to get compiled, so I'll get to that in a moment. So that's basically the typical recipe or template for creating, again, the Java native API. And this here talks about what I just said, so I'm not going to go over it in more detail. Now we build the API. Here are the problems. So here's the real meat of this whole thing. Okay? When we're building this implementation, which is going to be, in our case, called this long name, I generally like to give these things a long, like these files, the implementations of the C implementation of the Java code. I like to give them a long file name just so they better map onto what Java code was. So just to kind of explain this in a little more detail. Notice that this has some package name followed by this class name. Well, I tend to call this file package name _ class name.c or CPP, depending on the language of your choice. So that's the easy part. That's the simple mapping. But here's like I said, the meat of it. When we're dealing with different language environments, we have to basically deal with mapping. For example, how do Java methods map to C functions? Because methods not equal functions. You'll see that these functions are going to have to take some special parameters in order to basically do their jobs. Also, how do we map primitives? Because Java alone isn't the same as C alone. C alone is as big as the size of the word of the machine. So on most Android devices, it will be 32 bits, whereas Java alone is 64 bits no matter what platform you're on. So you have to take that into account. Java strings are not the same as C charrings. C charrings are basically, just a pointer to some memory that is null terminated, where every character is exactly 1 byte, whereas Java strings are objects that have pointing to an array, and that array has a known length, and inside of it, every character is 2 bytes, and it's UTF-16, so they're totally different. Java's arrays are not the same as well, so a byte array is not the same as just a pointer to memory in C. And basically, one of the main reasons for that is that in Java, objects or arrays, doesn't matter what they are, they represent logical references, as opposed to C pointers, which represent physical pointers to, or addresses in memory. Sure, it's not physical, it's actually virtually mapped, but as far as the application goes, it's physical. And so basically, the difference is that a garbage collector in Java or Android can move memory around, and your references are still valid. But whereas that cannot happen in C without having to update the references. Of course, the kernel can move pages around, in and out of whatever swappable storage. But point is, this is basically a major difference between C and Java, where C, you just know the memory is at some location. In Java, you just have a logical address that can be remapped at any time before it becomes physical. And finally, exceptions are different, right? Like the way you handle errors in C is not the same as the way you handle errors in Java. So those are the things that you have to worry about. So let me just then walk you through that implementation. So this is actually one long file that I broke down into sections so that I can basically point into the specific topics that are of interest. So first of all, you have to include your APIs that you're going to need. So you generally start with JNI.h. That was, like I said, the thing that defines the functions that will enable you to map the 2 language environments. And then the system functions that we need, for example, static files, and that would be a simple system function. Then Ndk APIs, in this case a logging function. This will enable us to log to ADB logcat, or to the log buffer that logcat can read. And then finally, the header of the library that we're actually wrapping, right? So you're going to have one of each here. Those are typical sets of includes. Now, how do you do logging? Well, logging, and again, this logging is defined using this Android log.h. Basically, can be done using this one function called Android log print. And the problem is that function is kind of long and complicated to use. So it's not uncommon to see people going and defining basically macros to deal with logging. So for example, I would define a log tag. For example, I call it jhead.c, and I would create a macro called loge that basically takes some sort of variable number of arguments and is mapped to calling the log print with the error, with our log tag, and the variable number of arguments, which are the ones that come from here. Okay? So of course, I know this looks a little crappy when it's like this. It really should look like this, but again, I'm having a problem with the projector display. You get hopefully the idea. And then one thing I do for debugging is I say, for example, if I have a variable called debug or something called debug defined, then log the debug is a real thing. Otherwise, debug is nothing. So it just becomes a null. Okay? And later on, if I wanted to just look at what this thing is doing, I can just go and filter for that particular tag. Now the fun starts. If you recall the API, one of the things that our API, let me actually just go back briefly to it. One of the things that our API needed to do is support returning a map given some sort of a string. Right? So notice this is native. How the heck is C code going to return a Java map? Well, let's take a look at that. This is basically where C can do reflection. So let me actually okay, there we go. So let me actually zoom out a little bit so we can see, there we go. Hopefully this is still big enough for you to see. So what do? I basically have a function in C called map_put. That function is going to take some sort of a map, and it's going to take a key and a value, and it's going to combine the two and call put. But there's a number of things we have to deal with. First of all, this key and these values are not, as we talked about, same as Java strings. These are null terminated single byte character arrays, as opposed to these glorified Java string objects that we know and love. So what do? We call on something called env, which is, think of it as a toolbox that's part of the JNI environment. We basically ask that this key be converted in something that is actually Java string that represents the key. And then we do the same thing for the value. And so we now have Java objects. These objects are, by the way, from this point forward, responsibility of the virtual machine or Dalvik to garbage collect when necessary. Now, there's a possibility there was not enough memory, so we have to test for them actually not being null, that's something you normally don't worry about in the Java world, but here you do. And now what we want to do is we want to call map, right? That was the map that we were given, .put. Okay, so how the heck do we call that? Well, we have to do reflection. Now, hopefully you guys, some of you know what reflection is from Java. Now you're going to see how you do reflection in C. In Java, you take a method that you previously looked up somewhere, and you say method.invoke, you specify the object and the arguments. Well, here we're kind of doing the same thing. We're saying call a method that basically is called on this object. This is the method ID, and here are the arguments. Now, the question though is, where the heck is this method coming from? So now let me just scroll up a little bit so I can explain this part. I have a function called Init Globals, which is going to be responsible for initializing some of the common structures that I'll keep on using over and over and over again. For example, one of them is this thing called look up a method, called put. So how does this work? Well, the first thing we're going to do is, just like Java has class.forName, we have to go and look up a class of Java util3 map. That's the map that I choose to use, because it's automatically sorted. And this is basically the thing that will give me a class. Of course, there's a possibility the class may not exist, so this doesn't just throw a no such class found exception or whatever the capture exception is. It basically just gives you null. It doesn't find it. Assuming that it does exist, then now what I do is I say, okay, give me a method in this class called init that takes nothing and returns void. This is actually another way of saying, give me the constructor. And then the next one, it says, give me the method called put. And this is where things get a little dicey. This is essentially how you write a signature in C. So what does this mean? All right, let me decipher this for you. These parentheses mean the parameters of the method. So what are the parameters of the put method? An object plus an object. And what's the return value? An object. So what do? I specify L to the semicolon means the class name, and then whatever I specify in between is the fully qualified class name. That's the parameter number 1. This is the parameter number 2, and this is the output. Right? So look for a function or a method called put in this class that takes an object plus an object and returns an object. That's basically what this means. Of course, there's a possibility of these things not existing, so I have to take that into account, and hopefully they do. And now what I need to do is I need to, you would think, well, I'm done, right? Because these things, these variables are all static, meaning they're global, right? But there's one challenge. Whenever in C world you access some sort of a Java object, in this case, this class is a Java object, all you get in the C world is a temporary reference to the Java object. Why temporary? Well, because the garbage collector within the virtual machine needs to be able to relocate this Java object at any time, and needs to be able to garbage collect it when he knows nobody else points to it. But because garbage collector doesn't know about you being able to point to it, doesn't know how long C code points to stuff, it assumes that as soon as you get some reference to an object, that reference is valid and you're considered a root pointer to that object for the duration of that method call, or in this case a function call. Essentially what that means is that this reference, my class or map class, is only valid within this block of code. So how do we make it last longer? We have to make it global reference. So we turn what was previously a local reference into a global reference. Again, I don't expect you to remember all of this, but I expect you to at least see what are the challenges when you're dealing with the two different worlds. The assumptions you have in the Java world versus the assumptions you have to live with in the C world. And so what this really means after this is that from this point forward, we own a reference to this object, and garbage collector promises not to collect it for us. Even though this is just a class, it's guaranteed not to collect it for us because we own it until we give it up. Otherwise, if we didn't do this, it would be illegal for us to reference this class afterwards. Alright, so now let's come back to this part. How do I make this method call? I simply say, on this object, call this method with these arguments. And that's it. The rest of it is just logic. This is just a convenience function. I'll show you in a moment how it gets used. Okay, how do the error handling? Here's, for example, a function that loads the image info utilizing JHead library. Okay, so first it goes and resets the file because, again, this is a global structure inside of JHead. Then goes and changes or resets some sort of more of the global structure, this thing called image info. Copies the function, the name of the file and whatnot, that's not even important. But then it tries to read the exit data. This is the actual call where we go into and say, okay, let's load the exit information, the meta info from this JPEG image. Well, what if this doesn't work? If this doesn't work, we don't want to just return -1 because Java isn't going to know how to deal with -1 because nobody will expect to go and look for -1. Instead, we want to throw an exception. So what do? We basically go and look up again the IOException class, and we then notice we're creating a simple stack-based array. We print a message into the stack-based array, fail to read JPEG file, blah blah blah, and then we throw that exception. Now, throwing an exception in Java would basically mean that this next line will be illegal because this will be unreachable code. But in C, this doesn't work like that because A, C doesn't support exceptions, but B, this exception that we quote-unquote threw here, all we did is we scheduled it to be thrown when we go back to the Java world. So essentially, you have to take on responsibility for interrupting the flow of code regardless of whether there may be a pending exception that will go back to, once you reach back to the Java world. Just another interesting thing to worry about. And again, this throw new is just a some sort of a helper function that JNI provides. So that's error handling. Now, mapping strings and arrays. So remember, this get thumbnail method is supposed to return an array, a byte array. Well, Java byte array isn't the same as C byte array. Right? C byte array is fixed, we know its size, and the address doesn't change. Whereas Java byte arrays are just logical pointers, and I should say that C, we don't know their size. Java byte arrays, we know their size, and they can be remapped in memory without us having to be notified about it, because again, it's logical versus physical. So, we also have a problem with this Java name. Like, so we're getting into this method a Java string that again is UTF-8 and it's UTF-16 and it knows its length and it's an object. It's not just a stupid byte character array. So we have to deal with this. So how do we deal with this? Well, first we convert the Java string into a C string. Now this internally will allocate memory. We'll literally do a malloc and they will copy data over because it needs to move from the one data structure to another. And because this allocates memory, we have to make sure that we have a corresponding release stat string. We don't quite use free because there's some additional accounting that we have to take in, JNI works, worries on our behalf about. So you just have to basically make sure that anything that allocates memory is followed by something that deallocates the memory in C because there's no automatic GC here. And there's a possibility that there wasn't enough memory when we wanted to make this conversion. Then we load the image info, and this, remember, is the previous function that can throw that exception. Well, there's a possibility that this failed. Despite the fact that there may be an exception, I have to basically go and escape further execution of the code so that takes me down here where I essentially get rid of anything that I had pending as far as memory goes. And then the rest of it is just simple, JHead code. I'm, for example, finding some section of data, and I'm looking for a thumbnail, and I figured out that this actually has a thumbnail. Okay, so now what? How do I actually take this code, the data that's available in C, and move it to Java? Well, I create a new Java byte array. Once I have that, I basically go and copy the region. I literally have to copy the C byte array into the Java byte array, and then I return the Java byte array. So this is something that normally you would just think, well, why the heck we're copying? But again, it's because of the fact that there are different semantics around how memory is used between the two languages. So we only have a few more minutes, so we're going to speed up a little bit so we can get out of here. This is the other function called getImageInfo. That is the one that's supposed to return a map. How do you return? How do you create an object in C? Well, remember how we previously looked up the constructor of a tree map, and we looked up the actual class of a tree map? Well, once we have both, we can essentially do class.newObject, or I should say constructor.invoke. That would be the equivalent in Java. So we're saying, hey, JNI, please create an object of this class using this constructor. And we now have the map. There's actually a possibility that this thing didn't load, and I should have actually had an if this is not null, then continue. So this is actually bad programming on my part. But then the rest of this is pretty much the same. Like I'm essentially calling the map put over and over and over again. Like this is an example of me saying, okay, map put into this map, key is camera make, and the value is image info camera make. And I keep on going and on over and over and over again. And when I'm done, I discard the memory. This is the memory related to the file name. This is the memory related to JHead. So again, I have to call this function to discard the memory. That's it. So last part is binding these things together. How the heck does Java find this code that I just showed you, the C code? Well, there are two ways of doing this. One way is to have this sort of naming convention, and so magically, if you follow this naming convention in C, then automatically something in Java that matches those names kind of merges together, fuses together runtime. That's one way. Another way is to basically take a more direct approach, which is implement a function called onload, or JNI onload, which is the Dalvik promises to invoke for you whenever you load this library for the first time. And in this function, we find the class, which is the one that has those native methods, and we say, once we have the class, we want to register with this class our methods, or I should say our functions. Now, what the heck is this? Well, here we have a table that basically says the following. Look for a Java method called getThumbnail that follows the following, that has this signature. Signature is, it has a string parameter and it returns a byte array, and map that to a C function called getThumbnail. Essentially, this is a function mapping table. This is a table that says this method maps to this function. And then we just call this register natives, and after that, this either works or blows up. If it blows up, it means we got it wrong. If it works, from this point forward, we are bound. Basically, the methods have been all resolved. And of course, we have to init our globals. That was the function I previously showed you. That's it. We could have used the Java age approach, which I'm not going to go over. You're welcome to kind of read this on your own. We just have to now compile it. This is basically the last piece. The last coding piece. We basically, in the Android.mk, we create another basically block of code that says, okay, clear previous global variables. We only have one source file to compile. The library that we're also going to statically compile with is called JHead. We also need to dynamically link at runtime with a library called liblog because we're using this logging functionality. And we want our code, our library, to be called JHead underscore JNI. The lib and the .so will automatically be added for us, and we build a shared library. Basically, this, if you want to think of it this way, this is nothing more than a glorified DSL, the domain-specific language. It's Android-specific for compiling stuff. By the way, it's called AOSP works as well. So you either do project build all, or you do Ndk build all, and this will now go and say, okay, let's compile this. Let's compile this stuff. And now let's compile this as a static library, and let's compile your JNI code as a shared library, which will automatically include a static library. And it does this 4 times because we have 4 different APIs, application binary interfaces. So basically, this is for RNV5, RNV7, this is x86, and the MIPS. So once this is done, we are now ready to use your code, your library. I'm not going to go over the application code because at this point we're in the Java land and you know how to get around. But this is an example of how you could write it, right? So you just call the static method and you either get an exception or you get a byte array. Once you have the byte array, you load it into a bitmap and you then stick it inside of some sort of a image view and you're done. That's how it shows, how that thing shows up. Or you just go and call this and you get a map of basically name value pairs that represent your exit information. That's it. Now, to summarize all of this, Ndk enables JNI. JNI is basically enables us to take advantage of C, C++ code, and Java code. In this case, specifically on Android. It's mostly used when you want to reuse existing code, and sometimes in the name of performance, but only when you can prove that it makes things better rather than worse. Doing this is not trivial. There are a lot of semantical differences that I just showed you. It's very brittle. All this reflection-based stuff is very brittle. You can break it at any point. There are a lot of security implications because of memory corruptions that can come into play. And you can end up with worse performance because of the overhead of going from the Java world and context switching into the JNI/native world. So with that said, thank you guys. Thanks for sticking around, and I'd be happy to answer any questions, but I'm probably going to get kicked out, so if you have any questions, maybe I'll take one or two, and then we'll just, take others offline. So, please.
I guess it's even harder to debug code that's built with JNI.
So, debugging, great question. So, first of all, there is a mechanism built into JNI on the Android debug platforms called check JNI that you enable through an option that essentially replaces the built-in JNI live implementation with one that has extra checks, so it fails more gracefully. So that's one thing. And the other thing is the Android Ndk toolchain does support GDB server and a client, and Eclipse can utilize it. So you can actually go and set up right now, double-click in your C code and set up breakpoints, and then run it through one of those project debug as Android application, and it'll hit those breakpoints and it'll stop and you'll be able to introspect your code. So just like you can do Java debugging, you can right from within Eclipse do C debugging. You cannot do that in Android Studio, at least I don't know how, with Android. I'm sure you could figure it out, but it doesn't work out of the box, let's put it that way. So yes, it's harder, but it's not the end of the world. And yes, I do recommend you take smaller incremental, changes to your code so when things blow up, you have a better context of what to fix. I can take one more question.
I don't think you got a room to collect anything
Any other questions? Please.
Yeah, so if the bulk of your application is written all in C and C++, and you have to interface with all these third-party libraries, does that mean I'm going to have to write a whole bunch of JNI bridges and stuff to interface with these other things?
So, short answer is yes. There are ways of going around that. Like, for example, you can make binder calls right from C if you know how. But you wouldn't be doing it using one of those supported APIs. You'd be risking your application not working well in the future. But short answer is, in most cases, the framework of your application is in Java, and then bits and pieces are written in C or C++, rather than the bulk of it being in C, C++, and maybe nothing or very little being in Java. That said, you can, especially if you're writing games, just do native activity, and then you have the information sensors and input stuff and whatnot. That's enough of the APIs for your game to be completely, entirely C++, for example, written. And then you can get away with that with writing zero Java. That said, your game would still run inside of a Dalvik virtual machine because the outer layer of your process still requires a lot of Java glue so you can interact with the system services that make it possible to even exist on Android. So you're not getting away from Java in terms of the runtime. It's always going to be there no matter what. Any Android application basically has Java, period. Like whether you see it or not. Any other questions? Alright, cool. So thank you guys for your attention. I'll be posting this probably within a couple of, well, maybe within a week or two. But the slides will also somehow link off of the GitHub page. So if you're interested, check out the Exify application, try it out. And like I said, I'll be posting slides. The slides probably there within a day or two. Thank you.